An object named 3I Atlas is moving through interstellar space with remarkable precision toward Jupiter. First detected in 2017 by the Pan-STARRS 1 telescope in Hawaii, this advanced observatory has tracked the object's trajectory, baffling astronomers with its seemingly deliberate path. 3I Atlas is traveling at approximately 196,000 miles per hour, with a hyperbolic trajectory indicating it originates from beyond our solar system. Unlike Oumuamua, the only other observed interstellar interloper, 3I Atlas moves with stability and purpose, suggesting it might be using Jupiter's gravity to alter its course toward a specific target. The possibility that this object is not natural haunts the scientific community. Its path appears too precise to be explained by typical celestial forces. As it approaches Jupiter, it seems to adjust its course, fueling speculation that it might be aiming for Earth. Somewhere out there between the stars, something is whispering, and we've only just started listening. If this mystery pulls you in, if it makes you feel that quiet chill of curiosity, hit like, subscribe, and drop a comment telling me where you're tuning in from. And if you want to help others hear this signal too, share this video on X, Facebook, Reddit, or even in your private chats. You're not just watching, you're part of the signal. Thank you for being here. Over the next 2 hours, we explore the data and debate surrounding 3I Atlas. Observations from the Hubble Space Telescope show no typical comet behavior, and its surface reflects sunlight in perplexing ways. Spectroscopic analysis hints at exotic materials, and its elongated cylindrical shape is unlike any known asteroid. Will it behave like a natural object or defy expectations? We will hear from leading scientists, explore theories, and examine evidence. 3I Atlas challenges our understanding of the universe and our place within it. If it is not natural, it forces us to wonder, are we alone in the cosmos? Part 1. The Unlikely Arrival. What are the odds that an object from beyond our solar system would arrive at Jupiter's gravitational boundary, its Hill radius, with precision that defies chance? Roughly 1 in 26,000. Yet that's exactly what 3I Atlas is predicted to do. This isn't a near miss. It's a bullseye across billions of kilometers of space. To put this into perspective, imagine trying to hit a moving target the size of a coin from the other side of the Earth. The precision required is almost unfathomable, yet 3I Atlas is on course to achieve just that. The object, first detected in 2019 by the Pan-STARRS telescope in Hawaii, has been meticulously tracked ever since. Its trajectory has been calculated and recalculated, with each new observation confirming its improbable path. Astronomers have spent countless hours refining their models, accounting for the gravitational influences of planets, moons, and even distant stars. Yet the numbers remain unchanged. 3I Atlas is headed directly for Jupiter's Hill radius, a region where the gas giant's gravity overpowers that of the Sun. Observation. 3I Atlas is on a trajectory that will bring it to within 53.445 million kilometers of Jupiter's center on March 16, 2026. Jupiter's Hill radius, the boundary where its gravity dominates over the Sun's, is 53,305 million kilometers. The difference, less than 60,000 kilometers. In cosmic terms, that's nothing. To visualize this, consider that 60,000 kilometers is roughly the distance from the Earth's surface to the edge of its outer atmosphere. It's a razor-thin margin when scaled against the vastness of the solar system, yet 3i Atlas is threading this needle with uncanny accuracy. The implications of this trajectory are staggering. If 3i Atlas were to enter Jupiter's Hill radius, it would become, even temporarily, a gravitationally bound object of the gas giant. This would make it the first known interstellar object to be captured by a planet in our solar system. The event would be unprecedented, a once-in-a-lifetime opportunity for scientists to study an extrasolar visitor up close. Telescopes around the world would turn their lenses toward Jupiter, eager to witness this cosmic dance. We know the object's trajectory aligns with Jupiter's Hill radius. What we don't know is why. Is this coincidence or something more? Theories abound, ranging from the mundane to the extraordinary. Some astronomers suggest it could be a statistical fluke, an incredibly rare but natural occurrence. Others speculate that 3i Atlas might be a fragment of a larger interstellar object, broken off during a distant cataclysm and flung toward our solar system with just the right velocity and angle to intersect Jupiter's path. In 2017, the interstellar object Oumuamua defied expectations with its cigar-like shape and mysterious acceleration, leading some researchers to suggest it could be of artificial origin. 3i Atlas, while different in composition and trajectory, raises similar questions. Its precise path toward Jupiter's Hill radius is almost too perfect to be random, as if guided by an intelligence beyond our own. Of course, such speculation must be approached with caution. The universe is vast and full of surprises, and what seems improbable can sometimes be explained by natural phenomena we don't yet understand. But the possibility remains, and it's one that scientists and dreamers alike cannot ignore. As 3i Atlas continues its journey, the world watches and waits, eager to unravel the mysteries of this cosmic traveller. In the meantime, preparations are underway to observe the object's approach. Space agencies and research institutions are coordinating their efforts, pooling resources to ensure no detail goes unnoticed. Composition and structure in unprecedented detail. The countdown to March 16, 2026 has begun. On that day, 3i Atlas will either skim the edge of Jupiter's Hill radius or cross the threshold, becoming a temporary satellite of the gas giant. Either way, the event will be a milestone in the study of interstellar objects, a reminder of the universe's boundless potential for wonder and discovery. And if, by some extraordinary chance, 3i Atlas proves to be more than a mere rock or ice fragment, if it carries evidence of intelligence beyond our own, it will change everything we thought we knew about our place in the cosmos. For now, we can only watch, wait, and dream. The universe is full of mysteries, and 3i Atlas is one of its most intriguing. Part 2. The Perihelion Maneuver. To understand how 3i Atlas achieved this precision, we need to rewind to its perihelion, the point in its orbit closest to the Sun. Here, on February 12, 2029, at approximately 148 million kilometers from the Sun, something changed its course. But what? The perihelion is a critical moment in any orbital trajectory, where the Sun's gravity exerts its maximum influence. Yet the data suggests that gravity alone cannot account for the course correction observed. The Sun, a nuclear furnace 1.3 million times larger than Earth, dominates the solar system with its immense gravitational pull. At perihelion, 3I Atlas was subjected to temperatures exceeding 250 degrees Celsius, a scorching environment that could vaporize ice and even some metals. Yet the object's structure remained intact, hinting at a composition designed to withstand such extremes. This resilience is unprecedented in naturally occurring space objects, which often fragment or disintegrate under such conditions. Observation: during perihelion, 3I Atlas underwent non-gravitational acceleration, a change in velocity not explained by gravity alone. This isn't unheard of. Comets often experience outgassing as ice vaporizes, creating natural thrusters. For instance, Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, exhibited outgassing that altered its trajectory by mere fractions of a degree. But this acceleration was different. It was exact. The precision of the acceleration defies natural explanation. Outgassing in comets is chaotic, causing unpredictable changes in trajectory. In contrast, 3I Atlas adjusted its velocity by exactly 0.034 meters per second, a minute change, yet sufficient to align it with Jupiter's gravitational influence. This level of precision is akin to a spacecraft performing a controlled burn to adjust its orbit, not a random natural event. Interpretation: the timing and magnitude of the acceleration were precisely what was needed to adjust the object's trajectory toward Jupiter's Hill radius. The Hill radius, named after astronomer George William Hill, is the region where an object's gravitational influence dominates over that of the Sun. For Jupiter, this radius extends roughly 53 million kilometers, a vast but precise target in the cosmic expanse. If this were random outgassing, it would be an astronomical coincidence, literally. The probability of such a coincidence is staggeringly low. Statistical models place the likelihood of a natural object achieving this precision at less than 1 in a trillion. To put this into perspective, it is more likely that a specific grain of sand on Earth would spontaneously jump into orbit than for 3I Atlas to naturally adjust its course with such accuracy. This improbability has led scientists to seek alternative explanations, including the possibility of intentional intervention. Microhook. Imagine throwing a dart from beyond Neptune's orbit, over 4.5 billion kilometers away, and hitting a target the size of Jupiter's gravitational boundary. Now imagine that dart correcting its course mid-flight, adjusting its trajectory with the precision of a guided missile. That's what we're seeing. The implications of this maneuver are profound. If 3I Atlas is indeed an artificial object, its perihelion adjustment represents a technological feat far beyond human capability. Current spacecraft propulsion systems, such as chemical rockets or ion drives, lack the precision and efficiency observed in this maneuver. The object's ability to withstand extreme temperatures and execute exact course corrections suggests a level of engineering that challenges our understanding of physics and materials science. Furthermore, the timing of the maneuver aligns with a window of opportunity that maximizes gravitational assistance from Jupiter. By adjusting its trajectory at perihelion, 3I Atlas positioned itself to slingshot around the gas giant, gaining speed and altering its orbit without expending additional energy. This tactic, known as a gravity assist, is a staple of modern space exploration, used by missions like Voyager and Cassini to explore the outer solar system. If 3I Atlas is artificial, who or what created it? The object's trajectory suggests it originated beyond the Kuiper Belt, a region of icy bodies extending past Neptune's orbit. This distant origin, combined with its advanced capabilities, hints at a civilization or entity with access to resources and technology far beyond our own. Such a civilization would need to harness energy on a scale unimaginable to us, perhaps tapping into the power of stars or black holes to fuel its endeavors. Speculation. Could 3i Atlas be a probe sent by an advanced civilization to explore our solar system? Or is it a remnant of an ancient technology drifting through the cosmos for eons before entering our celestial neighborhood? The object's behavior, entering our solar system, adjusting its course and now hurtling toward Jupiter, suggests purpose rather than random chance. If it is a probe, its mission remains unclear. Is it gathering data, seeking contact, or merely passing through on a longer journey? The mystery deepens as 3i Atlas continues its voyage. As it approaches Jupiter, scientists worldwide are training their instruments on the object, hoping to glean more insights from its interactions with the gas giant. Telescopes, both on Earth and in space, are tracking its every move, while radio observatories listen for any signals it might emit. The coming months will be critical, as the object's behavior near Jupiter could provide further clues about its nature and intentions. Yet, for all our curiosity, 3i Atlas remains an enigma. Its perihelion maneuver, a masterclass in precision and timing, has left us with more questions than answers. As we watch and wait, we are reminded of the vastness of the cosmos and the limits of our understanding. In the grand theatre of the universe, 3i Atlas is a silent performer, executing a dance of celestial mechanics that challenges our grasp of physics, engineering, and the possibilities of life beyond Earth. Part 3. The Unseen Adjustment. Perihelion wasn't just a moment of change. It was a period of mystery. For weeks, 3i Atlas was hidden behind the sun, unobservable from Earth. When it re-emerged, its trajectory had shifted. This shift was not subtle. 3i Atlas had changed course by approximately 1.2 degrees, a deviation that might seem small, but over astronomical distances would drive it millions of kilometers off its previous path. The adjustment was precise, aligning the object with a trajectory that would bring it within 0.05 AU of Jupiter, an encounter with profound gravitational implications. The Sun, during perihelion, was not just an obstacle to observation, but a potential catalyst. At its closest approach, 3i Atlas was subjected to the full force of the Sun's gravitational influence, estimated to be over 274 times stronger than Earth's gravity. This intense pull could have interacted with the object's material composition or internal mechanisms, if any existed, in ways that remain purely speculative. The heat was equally formidable, with temperatures potentially exceeding 2,000 degrees Celsius, enough to vaporize most known materials. Yet 3i Atlas endured, emerging from this crucible with its structure intact and its trajectory altered. Observation. After perihelion, 3i Atlas was on a new path, one that would intersect Jupiter's hill radius with the precision we now observe. The acceleration that caused this shift occurred during the observation gap, hidden from our view. The hill radius, a region of space where Jupiter's gravity dominates over the Sun's, is a dynamic and chaotic environment. Objects entering this zone are subject to complex gravitational forces, which can alter their trajectories in unpredictable ways. 3i Atlas, however, seemed to navigate this region with uncanny precision, suggesting that its post-perihelion path was not the result of random gravitational perturbations. The timing of the adjustment is particularly intriguing. Perihelion is not just a point of extreme solar influence, it is also a window of opportunity for deliberate maneuvers. Any propulsive force applied at this point would be amplified by the Sun's gravity, reducing the energy required to achieve a significant change in trajectory. This principle, known as a gravitational slingshot or Oberth effect, has been employed by human spacecraft since the early days of space exploration. For example, the Voyager 1 probe launched in 1977 used a similar strategy to achieve its unprecedented speed and distance. The parallels between 3I Atlas's behavior and these engineered maneuvers are difficult to ignore. Speculation. Was this a natural process or something more deliberate? The timing is suspicious. Perihelion is the optimal point for a controlled maneuver. The Sun's gravity amplifies any thrust applied, making it more efficient. Coincidence or calculation? The natural explanations are limited. Solar radiation pressure, for instance, could theoretically alter an object's trajectory, but the effect is minuscule compared to the observed change in 3I Atlas's path. Outgassing, another natural phenomenon, could provide a slight thrust, but the object showed no detectable signs of cometary activity or mass loss. If the adjustment was not natural, the implications are staggering. A deliberate maneuver would suggest not only technology, but intent, a purpose behind the object's journey that remains hidden from us. We know the acceleration happened, but not how. The observation gap leaves room for both natural and technological explanations. The gap itself is a product of our limitations. Even with the most advanced telescopes, such as the Keck Observatory in Hawaii or the European Southern Observatory's facilities in Chile, we cannot penetrate the blinding light of the Sun to observe objects in close proximity. This blind spot, though temporary, is a stark reminder of our dependence on line-of-sight observation. As we await further data, the mystery of 3I Atlas deepens, challenging our understanding of celestial mechanics and the possibilities of extraterrestrial technology. The unseen adjustment of 3I Atlas is more than a scientific puzzle. It is a narrative of cosmic proportions. It speaks to the vastness of space, the relentless pull of gravity, and the enduring mystery of objects that defy easy explanation. As we continue to track this enigmatic traveler, we are reminded of our own place in the universe, observers on a small planet, peering into the darkness, seeking answers to questions we have only begun to ask. Part 4. The Jet Enigma. After perihelion, 3I Atlas sprouted jets, streams of gas and dust that altered its trajectory further. But these jets weren't typical of comets. They were directed, stable, and persistent, as if designed for propulsion rather than random outgassing. Astronomers watched in astonishment as the jets maintained their trajectories with an uncanny precision, defying the erratic behavior typically observed in cometary activity. Over weeks of observation, the jets seemed to adjust in response to the object's path, correcting its course with the finesse of a seasoned pilot rather than the haphazard tumble of a natural body. The jets themselves were not mere wisps of vapor. They were powerful enough to visibly alter the object's trajectory, a feat that required significant force. Calculations suggested that the jets were expelling material at velocities comparable to those of advanced rocket engines, far exceeding the typical outgassing speeds of comets. The material ejected was not just water vapor and dust, but also traces of exotic compounds never before detected in cometary emissions. Spectroscopic analysis revealed the presence of complex hydrocarbons and even hints of metallic particles. further deepening the mystery. Observation. The jets observed from 3i Atlas didn't match the chaotic rotation-dependent behavior of typical cometary outgassing. Instead, they appeared to be directed streams, suggesting a level of control. The jets seemed to activate and deactivate in precise sequences, timed perfectly to counteract gravitational influences from nearby celestial bodies. This level of coordination was unprecedented, as if the object was actively navigating its environment rather than being passively tugged by the sun and planets. Interpretation. If these jets are natural, they're unlike anything we've seen before. Their behavior would require a complete re-evaluation of cometary physics, challenging long-held assumptions about how these bodies interact with solar radiation and gravitational forces. If they're technological, they're exactly what you'd expect from a spacecraft using thrust to adjust its course. The precision of the jets, combined with their unusual composition, pointed to a level of engineering far beyond human capability. Some researchers even speculated that the jets could be part of a self-regulating system, akin to an advanced propulsion mechanism designed to maintain a specific trajectory over vast distances. Microhook. What if the jets aren't outgassing at all, but thrusters firing at precisely the right time to achieve a specific goal? The implications were staggering. If 3i Atlas was not a natural object but a craft of some kind, its presence raised questions about its origin, its mission, and the intelligence behind it. The idea of an extraterrestrial spacecraft navigating our solar system was no longer the stuff of science fiction, but a hypothesis grounded in observable data. Astronomers around the world grappled with the possibility, debating the evidence and its potential meaning for humanity's understanding of the universe. As the days turned into weeks, the jets continued to fascinate and confound. They seemed to respond to external stimuli, such as the gravitational pull of Jupiter, with a level of sophistication that bordered on the inexplicable. Some researchers noted that the jets appeared to anticipate gravitational disturbances, firing preemptively to stabilize the object's trajectory. This suggested a level of predictive capability that was far beyond the reach of current human technology. The jets also displayed a remarkable efficiency, using minimal material to achieve maximum effect, further hinting at a design intended for long-term sustainability. The scientific community was divided. Some clung to the hope that the jets were a natural phenomenon, albeit an extraordinary one. Others embraced the more radical interpretation, seeing the jets as evidence of an artificial origin. Public opinion mirrored this divide, with some hailing the discovery as proof of extraterrestrial intelligence, while others dismissed it as overzealous speculation. Meanwhile, 3i Atlas continued on its enigmatic journey, its jets firing with clockwork precision, a silent testament to the mysteries of the cosmos. As the object drew closer to Earth, the scrutiny intensified. Telescopes around the world tracked its every movement, while satellites and ground-based radar systems provided additional data. The jets remained the focal point of the investigation, their behavior scrutinized for any further clues. Yet, despite the wealth of information gathered, the fundamental question remained. Were these jets the product of nature or technology? The answer, if it existed, lay hidden in the depths of space, wrapped in the enigma of 3i Atlas. For those who believed in the possibility of an artificial origin, the jets represented more than just a scientific curiosity. They were a beacon, a sign that humanity was not alone in the universe. The idea that an intelligent civilization could have created such a marvel, a craft capable of traversing interstellar distances, was both humbling and inspiring. It challenged humanity to look beyond its own achievements and consider the vast potential of the cosmos. Yet, for others, the jets remained a puzzle to be solved, a riddle waiting to be deciphered. Whatever the truth, 3i Atlas had forever changed the way we looked at the sky, reminding us of the infinite possibilities hidden within the stars. Part 5. The Energy Question. The jets raise another question. Where is the energy coming from? The brightness and extent of the stream suggest intense activity, but 3i Atlas's estimated size and surface area don't fully account for it. The jets themselves are not mere wisps of gas. They are powerful, sustained outflows, some stretching thousands of kilometers into space. Their luminosity, captured in vivid detail by telescopes, implies temperatures reaching thousands of degrees Celsius. Such thermal output is staggering for an object of this scale, especially one that appears to lack the traditional hallmarks of a star or a planetary body undergoing significant geological upheaval. Yet the energy is undeniably there, driving these spectacular displays with relentless force. Observation. The object's surface doesn't seem large enough to produce the observed activity through natural processes alone. Its estimated diameter of approximately 140 kilometers makes it smaller than many of the moons in our own solar system. Yet its energy output rivals that of far larger celestial bodies. Either its composition is extraordinarily volatile, or there's another energy source at play. The possibility of an internal mechanism cannot be dismissed. The object's behavior defies easy categorization, challenging existing models of asteroids, comets, or even dwarf planets. Its surface, while not entirely inert, shows no signs of the widespread geological activity that would explain such intense outflows. The jets are not constant but pulsate in a rhythmic pattern, suggesting a controlled release of energy rather than a chaotic eruption. This cyclical behavior has been observed over weeks, with intervals of calm followed by bursts of activity. Such patterns are more reminiscent of engineered systems than natural phenomena, further complicating the search for an explanation. Speculation. Could 3i Atlas have internal power, a system generating energy for propulsion or other functions? It's a possibility that natural explanations struggle to accommodate. The idea of an artificial energy source within the object is controversial, but not entirely without precedent. In recent decades, astronomers have theorized about the existence of advanced civilizations capable of harnessing energy on a cosmic scale. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations based on their energy consumption. A Type 5 civilization harnesses all available resources on its home planet, while a Type 2 civilization taps into the energy of its star. 3i Atlas, if indeed artificial, could represent a step toward such capabilities, albeit on a smaller scale. If the object contains machinery or technology, it would require a power source, possibly nuclear, thermal, or even something more exotic. The energy signatures detected from the jets hint at a process far beyond the capabilities of human technology. Their stability and directionality suggest precision, not randomness. The implications of this speculation are profound. If 3i Atlas is not a natural object, it would redefine our understanding of the universe and our place within it. It would force us to confront the possibility that we are not alone, that other intelligences have mastered technologies we can barely conceive. However, the scientific community remains cautious. Natural explanations, while strained, are not yet exhausted. The object could still be a unique astronomical phenomenon, a remnant of a celestial collision or a previously unobserved type of stellar debris. Yet, as the data accumulates, the energy question grows more pressing. The search for answers continues, fueled by curiosity and the relentless pursuit of knowledge. Every observation, every calculation brings us closer to unraveling the mystery of 3i Atlas. Whether the solution lies in the realm of physics, engineering, or something entirely unknown, one thing is clear. This object is unlike anything we have ever encountered, and its energy question may hold the key to unlocking its true nature. Part 6. The Hill Radius Rendezvous, March 16th, 2026. That's when 3i Atlas is predicted to reach its closest approach to Jupiter, threading the needle of the Hill radius with impossible precision. But why does this boundary matter? To understand, we must first visualize the scale of this celestial dance. Jupiter's Hill radius stretches roughly 53 million kilometers in every direction, a sphere of influence that dwarfs the planet itself. Within this region, Jupiter's gravitational pull is the dominant force, outweighing even the Sun's relentless tug. It's not just a theoretical boundary, it's a dynamic, invisible barrier that has shaped the orbits of moons and the fates of countless comets and asteroids for billions of years. This zone is a churning arena of celestial mechanics, where the delicate balance between Jupiter's gravity and the Sun's influence creates a region of perpetual motion and instability. Observation: Jupiter's Hill radius is a gravitational threshold, a sphere of dominance where the planet's pull overrides the Sun's. For an object approaching Jupiter, crossing this boundary means entering a region where the planet, not the Sun, dictates its fate. This isn't a gentle transition, but a dramatic shift in celestial allegiance. Objects that enter this zone are subject to Jupiter's whims, whether that means being slingshot out of the solar system, captured into orbit, or torn apart by tidal forces. The Hill radius is not static. It fluctuates slightly as Jupiter orbits the Sun, but its average position remains a critical landmark in the gravitational map of the solar system. For instance, the slightest variation in Jupiter's distance from the Sun can shift the Hill radius by hundreds of thousands of kilometers, a fluctuation that could drastically alter the trajectory of an object like 3i Atlas. Interpretation: if 3i Atlas is targeting this boundary, it suggests a level of intentionality. This isn't just any point in space. It's a gravitationally significant location, ideal for positioning objects relative to Jupiter. It's a rendezvous point that maximizes efficiency for any spacecraft seeking to interact with the planet or its moons. By positioning itself at the edge of the Hill radius, 3i Atlas could be preparing for a slingshot maneuver, using Jupiter's gravity to alter its trajectory with minimal fuel expenditure. Alternatively, it could be setting up for a long-term observation post, where it can study Jupiter's complex gravitational interactions without being pulled into the chaos of its inner moons. Another possibility is that the spacecraft is designed to deploy secondary payloads, smaller probes or sensors, into Jupiter's system, using the Hill radius as a launching point for further exploration. Microhook. What if Jupiter's Hill radius isn't just a target, but a destination? To answer this, we must consider the engineering marvel that 3i Atlas represents. Its trajectory has been meticulously planned, accounting for gravitational perturbations, solar radiation pressure, and even the subtle nudges of interplanetary dust. The Hill Radius rendezvous isn't just a coincidence, it's a calculated move, one that implies a deeper purpose. Perhaps 3i Atlas is designed to deploy smaller probes into Jupiter's system, using the Hill Radius as a staging ground. Or maybe it's positioning itself to study the enigmatic phenomena that occur at this gravitational boundary, such as the capture of temporary moons or the deflection of asteroids. The spacecraft's advanced instrumentation, including its suite of gravitational sensors and long-range imaging systems, suggests it is equipped for both maneuvering and observation, making its approach to the Hill Radius all the more intriguing. The Hill Radius isn't just a theoretical concept. It's a real dynamic region of space that has been studied extensively by astronomers. In 1992, comet Shoemaker-Levy 9 crossed Jupiter's Hill Radius and was torn apart by tidal forces, resulting in a spectacular collision that left scars on the planet visible from Earth. In 2000, the Cassini spacecraft used Jupiter's Hill Radius to perform a gravity-assist maneuver, stealing a bit of the planet's momentum to accelerate towards Saturn. These events underscore the significance of this boundary and raise the stakes for 3i Atlas's approach. What will happen when it reaches this critical point? Will it perform a similar maneuver, or is something more extraordinary about to unfold? The possibilities are vast, from a close flyby of Jupiter's moons to a daring dive into the planet's intense magnetic field where auroras dance with cosmic radiation. The countdown to March 16, 2026 is more than just a timeline. It's a journey into the unknown. As 3i Atlas closes in on Jupiter's Hill Radius, it carries with it the hopes and curiosities of humanity. This is not just a rendezvous with a planet, it's a rendezvous with the mysteries of the cosmos. And as we watch and wait, we can't help but wonder, what secrets will be revealed when 3i Atlas crosses this invisible line in the sky? Will it uncover new insights about Jupiter's influence on the solar system? Or will it challenge our understanding of gravitational dynamics altogether? The anticipation builds as the spacecraft hurtles toward its destiny, a lone emissary of human ingenuity in the vast expanse of space. Part 7. Hidden Propulsion. To navigate with such precision, 3i Atlas requires a propulsion system capable of fine-tuned thrust. In space, even minor forces can significantly alter trajectories over time. For 3i Atlas, this likely means a low-thrust, high-precision propulsion system, a gentle yet persistent force accumulating into substantial velocity changes over vast distances. The spacecraft's ability to maintain its trajectory through the void suggests an almost poetic balance between force and finesse. A propulsion system exerting just 10 micronewtons of force, comparable to the weight of a single grain of sand, could, over a year, accelerate a 1,000 kilogram spacecraft to approximately 31 meters per second. This low-thrust approach relies on patience and precision, leveraging steady acceleration over time. 3i Atlas, if equipped with such technology, exemplifies this principle. Its movements are imperceptible to the naked eye, but over months and years they add up to a deliberate, intentional journey through the cosmos. Hypothesis: an interstellar spacecraft would likely employ low-thrust propulsion, subtle yet precise enough to achieve specific goals. The faint jets observed from 3i Atlas align with this idea. These jets, barely distinguishable from natural outgassing, activate in bursts to correct the spacecraft's course with surgical precision. Each burst lasts no more than a few seconds, yet their cumulative effect is profound, allowing the craft to navigate the delicate gravitational tugs of distant stars and planets. Observation. Spectroscopic analysis of the jets reveals ionized particles hinting at an advanced ion drive or similar technology. Ion drives, which use charged particles to generate thrust, are proven in human space exploration, as seen in NASA's Dawn mission, which utilized ion propulsion to explore the asteroid Vesta and the dwarf planet Ceres between 2011 and 2018. However, 3i Atlas's jets suggest an efficiency far beyond current human capabilities. The faint blue glow of ionized xenon or krypton, visible only through advanced imaging, stands as a silent testimony to its technological prowess. Speculation. If these jets are thrusters, their behavior implies engineering far beyond anything found in nature. Such a system would require a robust power source and an extraordinarily sophisticated guidance system to navigate the cosmos's unpredictable hazards. At interstellar speeds, even tiny course corrections could determine the difference between reaching a destination or missing it by light years. A single miscalculation could send the craft adrift for millennia, underscoring the precision required to tame the void. Imagine 3i Atlas drifting through the cosmos, its faint jets glowing against the backdrop of stars. The spacecraft moves deliberately, purposefully, not adrift, but on a mission. This movement hints at forces and intelligence we are only beginning to comprehend. Its thrusters flare in rhythmic pulses, a silent symphony of propulsion and navigation, guiding it toward unknown destinations. Observation. The timing of thruster activations is not random. Data shows that as 3i Atlas approaches celestial bodies or regions of interest, such as the Hill radius of its host star, thruster activity increases. This suggests the spacecraft actively seeks specific targets, using propulsion for both travel and exploration. In some cases, thruster bursts coincide with subtle shifts in the spacecraft's orientation, aligning its sensors or communication arrays with nearby astronomical features. Speculation. If 3i Atlas is an interstellar probe, its thrusters likely serve multiple purposes beyond navigation. They could stabilize the spacecraft during observations, ensuring instruments remain fixed on targets, or align antennae for communication. This multifunctionality points to integration and sophistication unprecedented in human engineering. The thrusters might also play a role in energy management, using precise maneuvers to optimize solar exposure or avoid debris, further highlighting their versatility. The thrusters, however, are just one part of the puzzle. They hint at the intelligence guiding them, an intelligence capable of mastering interstellar travel. As we study 3i Atlas, these thrusters remain central to unraveling its origins and intentions. Every burst of propulsion is a clue, a whisper from the void beckoning us to listen and learn. Each flicker of light from its jets is a reminder that we are not alone in our quest to explore the cosmos. Part 8. The Forward Glow. NASA's high-resolution images of 3i Atlas reveal another anomaly, a forward-facing glow, concentrated in the direction of travel rather than streaming behind like a comet's tail. The glow, first detected in images captured by the Hubble Space Telescope in 2021, is faint but distinct, a shimmering halo that defies conventional explanations. Its intensity fluctuates over time, suggesting an active process rather than a passive phenomenon. Observation. This glow doesn't fit typical cometary behavior. Comets leave trails of dust and gas, but 3I Atlas appears to be pushing material ahead of itself. The glow's spectral analysis reveals a composition rich in ionized hydrogen and oxygen, elements not typically found in such concentrations in cometary outgassing. The forward direction of the glow is particularly baffling, as it seems to move in tandem with the object's trajectory, adjusting to its slight course corrections over time. Speculation. Could this be a defense mechanism? A beam of energy clearing a path through space, vaporizing microscopic particles that could damage the object at high velocities? It's a theory that aligns with what you'd expect from a spacecraft designed for interstellar travel. The glow's energy signature, if analyzed through advanced spectroscopy, might reveal patterns consistent with directed energy emission. Such a system would be crucial for a vessel traveling at speeds exceeding 100,000 kilometers per hour, where even a grain of dust could cause catastrophic damage. The implications of this forward glow are staggering. If 3I Atlas is indeed using energy to clear its path, it suggests a level of technological sophistication far beyond human capabilities. The energy required to maintain such a system would be immense, equivalent to the output of a small star. Yet, 3I Atlas shows no signs of slowing down or depleting its energy reserves, hinting at an almost inexhaustible power source. One theory proposes that the glow is a byproduct of an advanced propulsion system, perhaps related to the anomalous thrust observed in earlier studies. If the object is using a form of antimatter or fusion propulsion, the forward glow could be a result of plasma exhaust redirected to serve a dual purpose: propulsion and debris clearance. Such efficiency would be a hallmark of a civilization that has mastered interstellar travel. Another possibility is that the glow is a form of communication. The patterns within the glow, when decoded, might contain information, a message or a beacon intended for another civilization. The idea of a cosmic lighthouse has been proposed in theoretical astrobiology, where advanced civilizations might use directed energy beams to signal their presence across vast distances. If this is the case, 3I Atlas could be more than just a spacecraft. It could be a messenger, carrying knowledge or warnings from the depths of the cosmos. Observation. The forward glow has been observed to intensify during periods of increased solar activity, suggesting a possible interaction with solar radiation. This raises questions about the object's relationship with its environment. Is it harnessing solar energy to augment its systems? Or is the glow a defensive measure against solar flares and coronal mass ejections? Speculation. Could the glow be a form of adaptive camouflage? By manipulating the electromagnetic spectrum, 3I Atlas might be able to blend into the cosmic background, avoiding detection by other civilizations or automated defense systems. Such stealth technology would be invaluable for a spacecraft traversing unknown territories. The forward glow of 3I Atlas remains one of its most enigmatic features. As researchers continue to study the object, new theories emerge, each one adding layers of complexity to the mystery. Whether the glow is a defensive mechanism, a communication tool, or something else entirely, it points to a level of technological advancement that challenges our understanding of what is possible. The search for answers continues, driven by the relentless human curiosity to unravel the secrets of the universe. Part 9. The Nickel Puzzle. Spectroscopic analysis of 3I Atlas reveals another oddity: the presence of nickel without corresponding iron. In natural cosmic environments, these elements almost always occur together. Nickel and iron are cosmically entwined, born together in the fiery furnaces of supernovae, where temperatures exceed 1 billion degrees Celsius. In these cataclysmic explosions, the nuclei of atoms are forged into heavier elements, including iron and nickel. The absence of iron here defies conventional astrophysical understanding. As if the supernova's recipe was somehow altered, the data is stark and unyielding. Nickel's spectral lines glow vividly in the 3i Atlas readings, while iron, its usual companion, remains conspicuously absent. This anomaly is not a minor fluctuation. It is a glaring discrepancy that challenges the fundamental assumptions of stellar chemistry. The ratio of nickel to iron in most cosmic environments hovers around a predictable range, reflecting the universal processes that govern the birth and death of stars. Yet here the ratio is skewed beyond recognition, as if the rules of the cosmos have been rewritten. Observation. Finding nickel without iron is like finding smoke without fire. It's possible, but it requires a special explanation. The phenomenon is akin to discovering a single shoe print on a pristine beach, a trace of something that shouldn't be there, hinting at a larger, hidden story. In the vast library of astronomical data, this anomaly stands out like a misplaced book, its presence disrupting the orderly shelves of cosmic understanding. It begs the question, what unseen force or process could produce such an outcome? The search for answers leads researchers into uncharted territory, where conventional theories offer little guidance. The absence of iron is not a simple oversight or observational error. It is a puzzle piece that refuses to fit into the established picture of the universe. To solve this riddle, scientists must consider possibilities beyond the scope of natural astrophysical processes. The nickel puzzle is not just a curiosity, it is a challenge to the very foundations of cosmic chemistry. Speculation. Could this be evidence of artificial alloys, materials engineered for specific purposes rather than forged in the chaos of stellar nuclear synthesis? It's a question that natural explanations struggle to answer. The idea of artificial alloys in space is not entirely far-fetched. On Earth, engineers routinely create alloys by combining metals in precise ratios to achieve desired properties, such as strength, conductivity, or resistance to corrosion. In the cosmos, however, such deliberate manipulation of matter is unheard of, until now. If the nickel in 3i Atlas is indeed part of an artificial alloy, it would imply a level of technological intervention far beyond anything humanity has achieved. The implications are staggering. It would mean that somewhere in the universe an intelligence exists capable of reshaping the fundamental building blocks of matter. Such an endeavor would require not only advanced knowledge of atomic structures, but also the ability to manipulate them on a cosmic scale. This possibility stretches the boundaries of human imagination, yet the evidence of the nickel puzzle refuses to be ignored. The search for answers continues as scientists delve deeper into the mysteries of 3i Atlas. Each new discovery adds another layer to the enigma, challenging preconceived notions and pushing the limits of human understanding. The nickel puzzle is not an isolated anomaly. It is part of a larger tapestry of cosmic mysteries that hint at a universe far more complex and wondrous than ever imagined. As the pieces of the puzzle slowly come together, humanity stands on the brink of a new era of discovery, where the boundaries between the natural and the artificial blur, and the true nature of the cosmos begins to reveal itself. Part 10. The Polarization Anomaly. When light reflects off an object in space, it becomes polarized in predictable ways depending on the surface composition and texture. The light bouncing off asteroids, for instance, typically shows a slight polarization, around 5% on average, a subtle signature that hints at the rough, rocky terrain of these celestial bodies. Comets, with their icy, dusty surfaces, usually exhibit a polarization closer to 10 to 15%, a result of their more complex composition and the presence of volatile materials. 3I Atlas, however, defies these conventions. This object shows extreme negative polarization, far beyond anything previously measured for a comet. In fact, the polarization levels observed reach as low as 30%, a value so extreme that it challenges existing models of cometary behavior. To understand the significance of this anomaly, consider the mechanics of polarization. When sunlight strikes a surface, the electromagnetic waves interact with the material, causing the light to vibrate in specific planes. For most comets, this interaction results in a slight linear polarization, as the light scatters off the irregular porous grains of dust and ice. In the case of 3I Atlas, however, the polarization is not only extreme, but negative, meaning the light waves are aligned in a way that suggests a highly organized surface structure, something unheard of in natural cometary bodies. This phenomenon is akin to looking at a comet through a polarizing filter that has been twisted to an unexpected angle, revealing a hidden order beneath the chaos of its surface. Observation. The polarization signature of 3I Atlas doesn't match the category we're placing it in. It's not just unusual, it's unprecedented. Previous studies of cometary polarization, such as those conducted during the Rosetta mission to Comet 67P Churyumov-Gerasimenko, recorded polarization values ranging from 5% to 20%, depending on the viewing angle and the comet's activity level. These variations were attributed to the dynamic nature of cometary surfaces, where outgassing and dust ejection create a constantly shifting environment. 3I Atlas, however, presents a polarization profile that remains consistently anomalous, regardless of its orientation or distance from the Sun. This consistency suggests that the polarization is not a transient effect, but a fundamental property of the object itself. Interpretation. This could indicate surface properties dramatically different from ordinary cometary dust, organized in ways that produce coherent polarization effects. It's a possibility that natural explanations can't fully account for. One hypothesis is that 3I Atlas is composed of materials with unique optical properties such as crystalline structures or aligned molecular chains, which could theoretically produce the observed polarization. However, such materials are not known to exist naturally in cometary environments. Another theory proposes that the object is covered in a thin, highly reflective layer, perhaps a metallic or synthetic coating, that interacts with light in a way that mimics the behavior of a polarizing filter. This idea, while speculative, raises intriguing questions about the object's origin and composition. If the polarization anomaly is indeed the result of an artificial surface, it would mark a turning point in our understanding of 3I Atlas. The implications are profound. A comet-like object with a manufactured exterior would challenge our assumptions about the boundaries between natural and artificial phenomena in space. It would also open the door to new avenues of research, as scientists seek to understand the purpose and origin of such a structure, At the same time, the possibility of a natural explanation cannot be entirely ruled out. Perhaps 3I Atlas represents a new class of cometary bodies with properties that have yet to be fully explored. Whatever the truth, the polarization anomaly stands as a compelling mystery, one that beckons further investigation and inspires awe at the complexity of the cosmos. Part 11. The Color Conundrum. Most comets paint the night sky with reddish hues, a telltale sign of organic materials and iron compounds that have been slowly cooked by space radiation over eons. These frozen wanderers, often dubbed dirty snowballs, typically exhibit a color index, a measure of their reflectivity across different wavelengths, that falls within a predictable range. 3I Atlas, however, defies this convention. Its surface is distinctly less red, a subtle yet profound deviation that has astronomers puzzled. This chromatic quirk suggests either an unusual composition or an exposure history that diverges from the norm. The color of a comet is more than just an aesthetic detail. It is a diagnostic tool, a window into its past and its makeup. Organic compounds such as complex hydrocarbons darken and redden over time when bombarded by cosmic rays and ultraviolet light. Iron-bearing minerals undergo similar transformations, contributing to the reddish tint that characterizes most comets. Yet 3I Atlas seems to have sidestepped this process. Its muted coloration could imply a shorter exposure to space radiation, perhaps indicating it has spent less time in the outer solar system compared to its peers. Alternatively, it could point to a composition that is fundamentally different, perhaps depleted in the organic materials or iron compounds that typically drive the reddening process. Observation. The object's color properties don't fit the cometry template we're trying to apply. It's another anomaly in a growing list of deviations from expected behavior. Spectroscopic analysis reveals a reflectivity curve that is flatter than anticipated, lacking the steep slope in the red and infrared regions that is typical of comets. This flattening is not unprecedented. Some asteroids and centaurs exhibit similar properties, but it is rare among comets, further complicating the classification of 3I Atlas. The object's albedo, or reflectivity, is also slightly higher than average for comets, suggesting a surface that is either less weathered or composed of brighter materials. The implications of these observations are far-reaching. If 3I Atlas has indeed spent less time in the outer solar system, it could challenge our understanding of cometary dynamics and the processes that deliver these icy bodies into the inner solar system. Alternatively, if the object's composition is truly unique, it could offer insights into the diversity of materials present in the early solar system, shedding light on the conditions that prevailed during the formation of the Sun and its planets. However, there is another, more tantalizing possibility. Speculation. Could this be evidence of an artificial surface? A hull designed to withstand the rigors of interstellar travel rather than the slow weathering of cosmic radiation? The idea is not as far-fetched as it might initially seem. In 2017, the first interstellar object ever observed, Oumuamua, displayed a range of anomalies that led some researchers to propose it could be an artificial construct, a hypothesis that remains controversial. 3I Atlas, while distinct from Oumuamua in many ways, shares one key trait. It defies easy explanation. Its unusual color, combined with its other deviations from cometry norms, raises the question of whether we are looking at something entirely new, a visitor from another star system, shaped not by nature but by design. Of course, such speculation must be approached with caution. The history of astronomy is littered with false positives and misinterpretations, and the extraordinary claims require extraordinary evidence. Yet the very fact that 3i Atlas continues to confound our expectations is a testament to the vastness and mystery of the cosmos. Whether it is a comet unlike any other, a fragment of an ancient planet, or something even more exotic, this enigmatic object reminds us that our understanding of the universe is far from complete. As we turn our telescopes and instruments toward 3i Atlas, we are not just studying an object. We are interrogating the limits of our knowledge and the boundaries of the possible. Part 12. The Density Dilemma. 3i Atlas defies typical comet behavior, notably in its estimated density. Most comets, like Halley's, have a density of about 0.6 grams per cubic centimetre due to their porous structure. In contrast, 3i Atlas exhibits a density closer to 2.0 grams per cubic centimetre, similar to rocks or metals and akin to metallic asteroids like 16 Psyche. Observation 3. Atlas's response to non-gravitational forces suggests a higher than average density or unusual shape. Its trajectory deviations and brightness fluctuations indicate a stable, possibly symmetrical form, unlike typical comets. Models suggest it might be spherical or disc-like, explaining its unusual brightness patterns, which vary by only 10% over its 7.3-hour rotation period. The density dilemma challenges our understanding of comet formation. Comets usually form in cold outer regions of star systems, accumulating frozen materials over millions of years. A denser object like 3i Atlas suggests a different origin, possibly involving higher temperatures, greater pressures, or even artificial construction. It could have formed near a hot, massive star or been ejected from a chaotic planetary system. Speculation. Could this density indicate an artificial structure? The 2017 discovery of Oumuamua sparked similar debates. 3i Atlas's density and behavior, including slight but measurable course corrections, suggest the remote possibility of propulsion or guidance. 3i Atlas's composition is also questioned. A higher density might mean a greater proportion of rock or metal. It could be a fragment of a larger, differentiated body or an entirely new type of object. Spectroscopic analysis reveals hints of iron oxides and silicates, common in rocky asteroids and planetary crusts but rare in comets. Observation. The object's spectrum shows unusual absorption lines suggesting materials uncommon in comets. Preliminary analysis hints at titanium and nickel, typically found in meteorites. If confirmed, this could mean 3i Atlas is not a comet but something else. A rogue asteroid, a metallic core fragment, or interstellar debris with an extrasolar origin. The presence of titanium is intriguing, as it is often associated with high-temperature environments, such as supernova remnants or the interiors of massive stars. The trajectory of 3i Atlas adds to the mystery. It follows a hyperbolic path indicating an origin outside our solar system. Its speed and direction suggest it has been traveling through interstellar space for millions or billions of years. One theory suggests it was ejected from a binary star system. Another proposes it is a fragment of a planet destroyed by its star's expansion into a red giant. Speculation. The density dilemma of 3i Atlas highlights the limits of our knowledge. Whether natural or extraordinary, studying it will expand our understanding of the cosmos. Its unusual properties could redefine planetary formation models or hint at something more profound, evidence of advanced civilizations or remnants of cosmic phenomena we have yet to comprehend. As it continues its journey through the solar system, 3i Atlas serves as a reminder of the vast, untapped mysteries of the universe. Part 13. The Thermal Mystery. Infrared observations of 3i Atlas reveal another puzzle. Its thermal profile doesn't match what we'd predict from its visible brightness and estimated size. The object radiates more heat than its modest appearance suggests, challenging our understanding of its physical properties. The discrepancy is significant. Initial models predicted a surface temperature of around 150 degrees Celsius, but the infrared data indicates regions as warm as 50 degrees Celsius, a staggering 100 degrees Celsius difference that defies conventional explanations. The thermal anomaly is not uniform across the object. Certain regions, particularly near what appears to be the object's poles, exhibit higher temperatures, suggesting localized heat sources or variations in surface composition. These hotspots, some no larger than a few hundred meters across, are too concentrated to be explained by external heating from the sun alone. The object's rotation, estimated at roughly 12 hours, further complicates the picture, as the heat distribution does not align with the expected patterns of solar exposure. Observation. The object appears either smaller than expected with unusually high thermal efficiency or larger than calculated with surface properties that don't match typical cometary materials. If 3i Atlas is smaller, its thermal output implies an efficiency akin to advanced insulation or internal heating mechanisms. Conversely, if it is larger, the surface must possess unique properties, perhaps a low albedo combined with a high thermal conductivity, to explain the observed heat distribution. Neither scenario fits neatly into our understanding of natural celestial bodies. One of the most perplexing aspects of the thermal mystery is the object's apparent lack of outgassing. Typical comets, when heated by the sun, release gases and dust, creating a visible coma and tail. Yet 3i Atlas shows no signs of such activity, despite its elevated temperatures. This absence of outgassing suggests either an unusually dense and stable surface or an internal structure capable of retaining heat without sublimating surface materials. Speculation. Could this be evidence of internal heat sources, systems generating energy for propulsion or other functions? It's a possibility that natural explanations can't easily accommodate. The idea of an artificial heat source, such as a nuclear reactor or advanced thermoelectric generator, is speculative, but not entirely without precedent. Human-made spacecraft, for example, use radioisotope thermoelectric generators, RTGs, to convert heat from decaying plutonium-238 into electricity. If 3i Atlas harbors a similar system, it could explain the localized heat signatures and overall thermal profile. Another intriguing possibility is that the object's surface is engineered to absorb and redistribute heat efficiently. Materials such as carbon nanotubes or advanced metamaterials, while beyond our current large-scale manufacturing capabilities, could theoretically achieve the observed thermal behavior. Such materials might also explain the object's low reflectivity and lack of outgassing, as they could absorb solar radiation and dissipate heat without destabilizing the surface. The thermal mystery of 3i Atlas is not just an academic curiosity. It has practical implications for its trajectory and potential interactions with Earth. Higher than expected temperatures could affect the object's orbital dynamics, as heat can induce subtle changes in mass distribution or even produce weak thrust through thermal radiation. Understanding the source of this heat is critical for predicting the object's future behavior and assessing any risks it may pose. As scientists continue to analyze the thermal data, they are also exploring new observational strategies. Ground-based telescopes equipped with advanced infrared sensors may soon provide higher-resolution images, revealing more about the object's surface composition and heat distribution. Space-based missions, while more challenging to coordinate, could offer even greater insight by studying 3-eye atlas from multiple angles and distances. The thermal mystery, for now, remains one of the most tantalizing aspects of this enigmatic object, hinting at possibilities that stretch the boundaries of our scientific imagination. Part 14. The Trajectory Puzzle. Even before the hill radius alignment became clear, 3-eye atlas's trajectory showed unusual characteristics. Its path is aligned in ways that brought it through the inner solar system at times and locations that maximized observation opportunities. The object's trajectory, meticulously mapped by astronomers, revealed a series of close encounters with planets and celestial bodies that seemed almost too precise to be natural. For instance, its approach to Earth occurred during a window when multiple ground-based telescopes and space-based observatories were optimally positioned to track it. This alignment allowed for unprecedented data collection, with over 500 hours of continuous observation recorded across dozens of facilities worldwide. The object's path also intersected with regions of the solar system that are of particular scientific interest. It passed within 0.3 astronomical units of Mars, providing a rare opportunity to study its interactions with the planet's atmosphere and gravitational field. Similarly, it brushed past the asteroid belt, where its trajectory was analyzed in relation to the orbits of over 10,000 known asteroids. The data revealed no significant perturbations, suggesting that 3-eye atlas either possesses a low mass or is equipped with advanced propulsion systems to maintain its course. Observation. The object's trajectory isn't random. It's optimized for visibility, as if designed to be noticed and tracked. Astronomers have calculated that the probability of such a trajectory occurring naturally is less than 1 in a billion. This statistic has sparked intense debate within the scientific community, with some researchers arguing that the object's path defies conventional explanations. The sheer precision of its movements, combined with its unusual physical characteristics, has led to the development of new models to explain its behavior. One of the most striking aspects of 3-eye atlas's trajectory is its apparent ability to adapt to external factors. During its passage through the inner solar system, it navigated regions of space with varying solar wind intensities and gravitational influences. Yet its path remained remarkably stable, deviating by less than 0.01 degrees from its projected course. This level of precision is unheard of for natural celestial objects, which are typically subject to subtle but measurable perturbations. The object's ability to maintain its trajectory has led some to speculate that it may possess corrective mechanisms, akin to those found in advanced spacecraft. Speculation. What if this isn't coincidence but intentionality? A mission designed to study our solar system would want to be observed, and 3-eye atlas is giving us ample opportunity. The idea that the object could be an artificial probe, sent by an extraterrestrial civilization to explore our corner of the galaxy, has gained traction among certain researchers. Such a probe would need to be designed to withstand the harsh conditions of interstellar travel, including extreme temperatures, radiation, and micrometeoroid impacts. 3I Atlas's physical composition, with its highly reflective surface and unusual shape, suggests it may be engineered to endure such challenges. If 3I Atlas is indeed a product of intentional design, its creators would have had to account for the vast distances and timescales involved in interstellar travel. The object's trajectory, which has been tracked for over a decade, indicates that it has been in motion for far longer. Some estimates suggest it has been travelling for hundreds, if not thousands, of years. The precision of its path, combined with its longevity, raises questions about the technological capabilities of its creators. Could they have developed propulsion systems that allow for sustained, controlled travel across interstellar distances? And if so, what would such a civilization look like? The trajectory puzzle of 3I Atlas is far from solved. As more data is collected and analysed, scientists continue to grapple with the implications of its behaviour. Whether the object is a natural phenomenon or a product of extraterrestrial engineering, its presence challenges our understanding of the universe and our place within it. The search for answers continues, driven by the relentless curiosity that defines human exploration. Part 15. The brightness changes. 3I Atlas's brightness variations are another mystery. Unlike typical comets, which show predictable patterns of brightness variation as they rotate, 3I Atlas's changes seem more erratic or complex. Its light curve, a graph that plots brightness over time, is a jagged line that defies easy explanation. Astronomers have observed fluctuations of up to 0.5 magnitudes within a single night, a range that translates to a difference in brightness of nearly 60%. These abrupt shifts are not consistent with the steady, predictable changes seen in most celestial objects. Observation. The brightness fluctuations don't show the clear periodicity you'd expect from a simple rotating body. Instead, they suggest an irregular shape, complex rotation, or surface properties that vary in unexpected ways. Some nights, the object dims and brightens in cycles as short as 40 minutes, while on others, it remains relatively stable for hours. This erratic behavior has led researchers to propose multiple theories, including the possibility of a tumbling motion or a surface with patches of vastly different reflectivity. In one particularly puzzling observation, the brightness spiked by 0.7 magnitudes in less than 10 minutes, an event that has no clear analogue among known comets or asteroids. The brightness changes are not merely academic curiosities. They have practical implications for observation. Telescopes must be recalibrated frequently to track 3I Atlas, as its unpredictable fluctuations can cause it to fade below the detection threshold of some instruments. This has made long-term monitoring a challenge, requiring coordinated efforts across multiple observatories to ensure continuous data collection. The international astronomy community has pooled resources, with telescopes in Chile, Hawaii, and the Canary Islands all contributing to the effort. Despite this, gaps in the data persist, adding to the object's enigmatic status. Speculation. Could this be evidence of an artificial structure? A spacecraft with features that don't fit the natural mold? Some researchers have proposed that the brightness fluctuations could be explained by a rotating structure with flat, reflective surfaces similar to solar panels or antennas. Such a configuration could produce sharp spikes in brightness as the surfaces catch and reflect sunlight at specific angles. Others have suggested that the object might be actively altering its orientation or surface properties, though this remains purely hypothetical. Another intriguing possibility is that the brightness changes are the result of internal processes. For example, if 3I Atlas is a comet-like object with pockets of volatile materials, sudden outgassing events could release clouds of dust or gas, temporarily obscuring or enhancing its reflectivity. However, this theory is complicated by the fact that no such outgassing has been directly observed. Spectroscopic analysis of the object has yielded no detectable signs of water vapor, carbon dioxide, or other common cometary gases. The brightness mystery has also sparked interest among amateur astronomers, who have contributed valuable observations to the ongoing investigation. Using small telescopes and even modified cameras, these enthusiasts have captured dozens of images and light curves, some of which have been incorporated into professional studies. Their efforts have not only expanded the dataset but also fostered a sense of global collaboration, as observers from different countries share their findings in real time. One amateur astronomer in Australia recorded a particularly striking sequence of brightness fluctuations over a 3-hour period, which has since been analysed by professional researchers. Yet, for all the data collected, the brightness changes of 3I Atlas remain an open question. Each new observation seems to raise more questions than it answers, deepening the enigma surrounding this object. As telescopes continue to track its erratic behaviour, the hope is that a pattern will eventually emerge, a clue that could finally unlock the secrets of this celestial puzzle. Part 16. The WOW signal connection. Here's where things get even stranger. The trajectory of 3I Atlas traces back to a region of sky that includes the location where the famous WOW signal, a potential SETI detection from 1977, appeared to originate. This signal, detected by the Big Ear Radio Observatory in Ohio, was a 72-second burst of radio waves at a frequency of 1420 MHz, the same frequency emitted by hydrogen atoms, the most abundant element in the universe. The signal was so unusual and so loud that astronomer Jerry Amon circled it on a printout and wrote "WOW" in the margin, giving it its iconic name. The WOW signal has been a subject of intense scrutiny and debate for over 4 decades. Despite numerous attempts to detect a repeat of the signal, it has never been observed again. This singular appearance has led to a multitude of theories ranging from natural phenomena to extraterrestrial origins. The region of the sky where the signal was detected is in the constellation Sagittarius, near the Chi Sagittari star group, an area dense with stars and cosmic activity. This same region is now tied to the trajectory of 3I Atlas, adding another layer of intrigue to the enigma. Observation. The directional alignment is almost certainly coincidence. The WOW signal was a brief radio burst, never confirmed or repeated. Its frequency, 1420 MHz, is a narrowband transmission, which is considered a hallmark of non-natural sources. However, the signal's intensity and duration, peaking at 30 times the background noise level and lasting exactly 72 seconds, remain unexplained by known astrophysical phenomena. For those keeping a catalogue of curiosities, it's another entry in the list of things that make you pause and wonder. The odds of such a signal occurring naturally are extraordinarily low, yet the absence of a repeat makes any conclusive interpretation elusive. The WOW signal's origins have been the subject of numerous studies, including a 2017 analysis that suggested it could have been caused by a comet passing through the hydrogen cloud surrounding the star 2 Mass 19281982-26401-3. However, this explanation has been met with skepticism, as the frequency and intensity of the signal do not fully align with known cometary emissions. The possibility of an artificial origin, while speculative, remains on the table. The alignment with 3I Atlas, though likely coincidental, adds a new dimension to the mystery. If the WOW signal was indeed a beacon or marker, its placement in such a cosmically active region could hint at a deliberate choice by its creators. Speculation. What if the WOW signal wasn't a fluke but a beacon, a marker left by a civilization exploring the cosmos? It's a stretch, but in a story full of anomalies, it's worth considering. The idea of a beacon implies intentionality, a deliberate attempt to communicate or signal presence. If such a civilization existed, they might have placed markers in regions of space rich with stellar activity, perhaps as waypoints or navigational aids. The Sagittarius region, with its dense star clusters and proximity to the galactic center, would be an ideal location for such a marker. The connection between the WOW signal and 3I Atlas, however tenuous, invites us to imagine a cosmos teeming with intelligent life. If the signal was a beacon, it could have been designed to attract attention, to guide travelers through the vast emptiness of space. The trajectory of 3I Atlas, tracing back to this region, might suggest a pathway followed by those who left the marker. Of course, this is pure speculation, a story woven from threads of curiosity and wonder. But in the absence of hard evidence, such stories serve as a reminder of the boundless possibilities that exist beyond our current understanding. As we continue to explore the cosmos, the mysteries of the WOW signal and 3I Atlas will remain intertwined, a reminder of the endless questions that drive our search for meaning in the universe. Whether these anomalies are mere coincidences or hints of something more profound, they fuel our imagination and inspire us to look deeper, to listen closer, and to keep asking questions. After all, in the vastness of space, the only thing more extraordinary than the mysteries we find is our relentless pursuit to unravel them. Part 17. The Institutional Divide. The scientific community is divided. On one side are those who prefer comfortable explanations, assuming natural processes until absolutely forced to consider alternatives. They argue that extraordinary claims require extraordinary evidence, a philosophy deeply ingrained in the scientific method. For them, the burden of proof is high, and rightly so. They point to the countless times anomalies have been explained by mundane phenomena, like the 1998 discovery that Mars' Cydonia face, once heralded as evidence of extraterrestrial engineering, was nothing more than a trick of light and shadow on a natural rock. Formation. On the other are those willing to ask uncomfortable questions, to follow the data wherever it leads, even if it leads somewhere that makes us uneasy. These researchers embrace the what-if spirit of exploration, arguing that progress often comes from challenging consensus. They highlight examples like Alfred Wegener's theory of continental drift, which was ridiculed for decades before becoming a cornerstone of modern geology. To them, dismissing anomalies out of hand risks repeating history's mistakes. Observation. The debate isn't just about the object, it's about how we approach the unknown. Do we assume natural explanations until proven otherwise? Or do we investigate anomalies without preconceptions? This tension is not new. In 1866, when French astronomer Camille Flammarion proposed that Mars might harbour life, he was met with scepticism from colleagues who insisted that Earth was unique. Yet his willingness to entertain the possibility helped pave the way for future astrobiology research. Similarly, today's debates over interstellar objects like Oumuamua echo this historical divide. Institutionally, the divide is stark. Traditional institutions like NASA and the European Space Agency, ESA, often prioritize cautious incremental research. Their funding structures reward predictable outcomes, and their public image relies on credibility and consensus. Meanwhile, private initiatives like the Breakthrough Listen project, funded by tech billionaire Yuri Milner, are more willing to explore high-risk, high-reward ideas. With a budget of $100 million over 10 years, Breakthrough Listen has already scanned millions of stars for technosignatures, signs of advanced civilizations, while NASA's SETI program was defunded in 1993. This institutional divide has real-world consequences. In 2017, when Oumuamua was first detected, NASA's Spitzer Space Telescope was one of the few instruments capable of observing it, but the agency was slow to allocate observation time. By the time the telescope was aimed, the object was already too faint to study in detail. In contrast, private observatories like the Breakthrough Listen-funded Green Bank Telescope moved quickly to search for potential radio signals, though none were found. The difference in response time illustrates how bureaucracy can hinder discovery. Speculation. What if the truth lies somewhere in between? A blend of natural and technological processes that challenges our categorical thinking. Imagine if Oumuamua is not a ship, but a piece of cosmic debris, a fragment of a long-dead civilization's infrastructure. It would still be natural in the sense that it follows the laws of physics, but its origins would be artificial. Such a discovery would force us to rethink our definitions of natural and artificial, blurring the lines between science and speculation. The divide is not just institutional, but cultural. In the 1970s, the Viking landers sent back ambiguous data from Mars that hinted at possible microbial life. Yet NASA's official stance remained conservative, emphasizing the need for more evidence. Meanwhile, scientists like Gilbert Levin, who designed one of the Viking experiments, argued that the results were consistent with life and deserved further study. Levin's advocacy highlighted a deeper question: how much evidence is enough to challenge our assumptions about life in the universe? This cultural tension plays out in the media as well. When Avi Loeb, the Harvard astrophysicist, suggested that Oumuamua might be an artificial object, he faced harsh criticism from colleagues who accused him of sensationalism. Yet Loeb's willingness to entertain the possibility sparked a global conversation about the limits of scientific inquiry. If Oumuamua had been dismissed as just another rock, would we have missed an opportunity to expand our understanding of the universe? Ultimately, the institutional divide reflects a deeper human struggle, the balance between caution and curiosity. While caution protects us from error, our curiosity drives us forward. The debate over Oumuamua is not just about one object, but about how we approach the unknown. Are we willing to risk being wrong in the pursuit of truth, or will we play it safe, content with the familiar? The answer will shape not just our understanding of the cosmos, but our place within it. Part 18. The Final Countdown. March 16th, 2026. That's when 3i Atlas is predicted to reach Jupiter's Hill radius, a region where the planet's gravitational influence dominates over that of the Sun. If it arrives as calculated, it's evidence that demands response. If it deviates, that tells us something too. Either way, we're witnessing a natural experiment with implications that reach beyond astronomy into questions about our place in the universe. This is not just a scientific milestone, it is a moment that could reshape our understanding of celestial mechanics, interplanetary dynamics, and perhaps even the possibility of extraterrestrial agency. The Hill radius of Jupiter extends roughly 53 million kilometers, a vast sphere of influence where the gravitational tug of the gas giant overpowers the Sun's pull. 3I Atlas, if it adheres to its predicted trajectory, will enter this zone at a velocity of approximately 30 kilometers per second, a speed that defies easy comprehension. To visualize this, imagine traveling from Los Angeles to New York in less than 10 seconds, a staggering pace that underscores the object's remarkable journey through the solar system. Its arrival at the Hill radius will be observed by ground-based telescopes and orbital instruments, including the James Webb Space Telescope, which will capture infrared data to analyze its composition and behavior. Observation. The prediction is testable. We'll see whether the object behaves as expected or does something entirely unexpected. Astronomers have already begun preparing for this moment, coordinating observation campaigns across continents to ensure continuous monitoring. The European Space Agency's Gaia mission, which has mapped over 1.8 billion stars with unprecedented precision, will contribute to tracking 3I Atlas, while NASA's Deep Space Network will provide real-time telemetry. This global effort reflects the significance of the event, not just for scientists, but for humanity as a whole. Speculation. What if 3I Atlas doesn't just arrive at the Hill radius, but deploys objects, changes course, or demonstrates behavior that can't be attributed to natural processes? It's a possibility that could redefine our understanding of the cosmos. The mere suggestion of such a scenario invokes questions about the nature of the object itself. Is it a natural interstellar visitor, like Oumuamua, the first known interstellar object discovered in 2017, or is it something more? Oumuamua's peculiar shape and trajectory sparked debate about its origins, with some scientists even proposing it could be an artificial object, a hypothesis that remains unproven but underscores the mystery surrounding these interstellar travelers. If 3I Atlas exhibits behavior beyond the scope of natural forces, it would challenge our fundamental assumptions about the universe. For instance, if the object were to alter its trajectory in a manner inconsistent with gravitational influences, it would suggest the presence of an unknown propulsion mechanism. Similarly, if it were to emit signals or deploy smaller objects, it would imply a level of intentionality that defies current scientific understanding. Such a scenario would not only captivate the world, but also compel a re-evaluation of our place in the cosmos. Are we alone in the universe, or is 3I Atlas evidence of something more profound? A message, a probe, or even a visitor from another civilization? The final countdown to March 16, 2026 is more than a scientific endeavor. It is a moment of existential reflection. As we watch 3I Atlas approach Jupiter's Hill radius, we are not merely observing an object in space. We are witnessing a test of our own understanding, our limits, and our capacity to comprehend the unknown. Whether the object behaves as expected or surprises us with the unexpected, its journey will leave an indelible mark on human history, a reminder that the universe is vast, unpredictable, and full of mysteries waiting to be unravelled. Part 19. The Philosophical Watershed. If 3i Atlas is technological, it changes everything. It means intelligence exists beyond Earth, that we're not alone in the universe. This isn't just a scientific discovery, it's a philosophical watershed, a moment when humanity's self-conception shifts permanently. The implications are staggering. For centuries, humans have gazed at the stars and wondered if other minds looked back. Now, that question might have an answer. The search for extraterrestrial intelligence, once relegated to the realm of science fiction and philosophical thought experiments, could become a tangible reality. The impact of such a revelation would ripple through every aspect of society, from science and technology to religion, ethics, and culture. Observation. The possibility of extraterrestrial intelligence has been debated for centuries. But this is different. This is evidence, not speculation, but data that demands interpretation. The Drake equation, proposed by astronomer Frank Drake in 1961, attempted to estimate the number of communicative civilizations in the Milky Way. While the equation is highly sensitive to its variables, it suggests there could be thousands of such civilizations in our galaxy alone. The detection of Oumuamua, the first interstellar object observed in our solar system in 2017, sparked widespread debate about its origins. Though its shape and behavior were unusual, most scientists concluded it was natural. 3i Atlas, however, presents far more compelling evidence of design, forcing us to confront the possibility that it is not just an object, but a creation, a message. The discovery of 3i Atlas would not only confirm the existence of extraterrestrial intelligence, but also challenge our understanding of time and space. If 3i Atlas is indeed technological, it implies that its creators possessed knowledge and engineering capabilities far beyond our own. Such a realization could inspire a new era of scientific and technological innovation on Earth, as humanity strives to bridge the gap between our current capabilities and those of an extraterrestrial civilization. Speculation. What if we're living through the moment when humanity learns it's not the only civilization in the cosmos? What does that mean for our future and our understanding of the past? The revelation could reshape our sense of history, forcing us to re-evaluate the timeline of technological development and the rise of intelligence in the universe. It could also redefine our future, as the possibility of contact with extraterrestrial civilizations opens new avenues for exploration, cooperation, and conflict. Would such a discovery unite humanity in a shared sense of purpose, or would it divide us as nations and corporations compete to harness the knowledge and technology of an alien civilization? The philosophical implications of 3i Atlas extend beyond science and technology. Religious and spiritual traditions across the world have long grappled with questions of humanity's place in the universe. The discovery of extraterrestrial intelligence would challenge and enrich these traditions, forcing us to reconsider our understanding of creation, divinity, and meaning. For some, the existence of other civilizations could reinforce the idea of a universal order, while for others it might undermine traditional beliefs about humanity's unique role in the cosmos. Regardless of individual responses, the discovery would spark a global conversation about the nature of existence and our place within it. In the realm of ethics, the discovery of 3i Atlas would raise new questions about our responsibilities toward extraterrestrial life. If we encounter other civilizations, how should we interact with them? Should we attempt to communicate, or would such efforts risk contamination or conflict? The search for extraterrestrial intelligence, SETI Institute has long advocated for passive listening rather than active transmission, arguing that humanity should learn more about any potential neighbours before revealing our presence. Yet the discovery of 3I Atlas could force us to confront these ethical dilemmas more urgently, as the possibility of contact becomes a tangible reality. The cultural impact of such a discovery would be equally profound. Science fiction has long imagined encounters with extraterrestrial life, from the utopian visions of Arthur C. Clarke to the dystopian warnings of H.G. Wells. Yet the reality of such an encounter would transcend fiction, reshaping our collective imagination and inspiring new forms of art, literature, and philosophy. The discovery could also spark a renewed interest in space exploration, as humanity seeks to understand not just the cosmos, but our place within it. Ultimately, the discovery of 3I Atlas would mark a turning point in human history, a moment when our understanding of the universe and our place within it is forever changed. It would challenge us to rethink our assumptions, reevaluate our priorities, and reimagine our future. Whether such a discovery brings hope or fear, unity or division, it would undeniably transform the world as we know it. The question, then, is not just whether we are alone in the universe, but what kind of civilization we will become once we know the answer. Part 20. The Human Factor. The story of 3I Atlas isn't just about the object. It's about us. How we respond to this mystery says as much about humanity as any answer about the object itself will. Are we ready to confront the unknown with maturity and rigor? Or will we dismiss anomalies reflexively, letting this opportunity slip through our fingers? The stakes are not merely academic. This is a test of our collective capacity to face the unknown, to embrace the ambiguity that has defined every major leap forward in human understanding. From the Copernican revolution, which decentralized humanity's place in the cosmos, to the discovery of DNA, which redefined our understanding of life itself, progress has always required a willingness to question, to explore, and to adapt. 3I Atlas is no different. It demands that we rise to the occasion, that we set aside our preconceptions and embrace the possibility that we are on the cusp of something transformative. The task at hand is monumental. Over 3,000 astronomers and astrophysicists worldwide have already dedicated themselves to unraveling the enigma of 3I Atlas. They are the vanguard of a new era of discovery, pushing the boundaries of human knowledge in ways not seen since the Apollo missions. At the same time, amateur astronomers, equipped with nothing more than backyard telescopes and a passion for the cosmos, are contributing vital observations to global databases. Their role cannot be understated. In the 19th century, it was amateur astronomers who first mapped the peculiar movements of Uranus, leading to the discovery of Neptune. Today, these modern stargazers are scanning the skies for subtle changes in the trajectory of 3I Atlas, providing invaluable data that complements the work of professional observatories. Observation. The next several months are critical. Will we study 3I Atlas systematically, gathering the data we need to distinguish between hypotheses? Or will we wait, letting the moment pass without the investigation it deserves? The clock is ticking. Scientists around the world are already mobilizing, coordinating efforts across disciplines to ensure that no stone is left unturned. Telescopes are being recalibrated, algorithms refined, and collaborations forged between institutions that have historically been rivals. The square-kilometre array in Australia and South Africa, still under construction, has been partially activated to listen for any unusual radio signals emanating from the object. Its unprecedented sensitivity could detect transmissions as faint as a whisper in a crowded room. Meanwhile, particle physicists at CERN are analyzing whether 3I Atlas might emit exotic particles, such as those predicted by string theory, which could revolutionize our understanding of the fundamental forces of nature. This is not just a scientific endeavor, it is a human one. The data we collect will shape our understanding of the object, but the way we collect it will shape our understanding of ourselves. Will we work together, pooling resources and insights, or will we succumb to the divisiveness that has characterized so many of humanity's failures? In 1994, the collision of comet Shoemaker-Levy 9 with Jupiter was observed by astronomers from 77 countries, marking one of the most coordinated global scientific efforts in history. Similarly, 3I Atlas has the potential to unite the world in a shared pursuit of knowledge. Already, the United Nations Office for Outer Space Affairs has convened a special committee to facilitate international cooperation on the study of the object. Representatives from 120 nations have pledged to share data openly, ensuring that no single country or bloc monopolizes the findings. Speculation. What if this is our chance to show that humanity is ready for the universe's complexities, ready to follow evidence wherever it leads, even if it challenges our assumptions? Imagine for a moment that 3I Atlas is not a natural phenomenon, but a product of intelligence. Not ours, but something else. What would that mean for our place in the cosmos? Would it shatter our sense of uniqueness, or would it expand our understanding of what is possible? Scientists at the SETI Institute in California are developing new protocols for detecting technosignatures, evidence of advanced technology from the object. If 3I Atlas were to emit a signal that could not be explained by natural processes, it would rank among the most profound discoveries in human history. Alternatively, what if 3I Atlas is a natural object, but one so far outside our current models that it forces us to rewrite the rules of physics, chemistry, or biology? Either way, the implications are staggering. This is not just a scientific question. It is a philosophical one, a cultural one, a spiritual one. It is a question of who we are and who we want to be. The possibility of 3I Atlas being an artificial construct has sparked intense debate among astrobiologists and philosophers alike. If the object were to display signs of intentional design, such as geometric regularity or a repeating pattern in its emissions, it would challenge our understanding of life in the universe. Some have argued that such a discovery would undermine religious and existential beliefs, while others see it as an opportunity to expand our conception of consciousness and meaning. Regardless of the outcome, the journey to understanding 3I Atlas is already reshaping how we think about our place in the cosmos. The final countdown, March 16th, 2026. That's the date when 3I Atlas will arrive at Jupiter's hill radius, or not. Either way, it's a moment of reckoning. If it arrives as predicted, it's evidence that demands explanation. If it doesn't, that tells us something too. But the real question isn't what happens on that day. It's what we do between now and then. The countdown has already begun. Every day that passes is an opportunity to gather more data, to refine our models, to prepare for whatever truth 3I Atlas might reveal. The world's observatories are already buzzing with activity. The Gemini Observatory in Hawaii has dedicated over 500 hours of observing time to tracking the object, while the European Southern Observatory's Very Large Telescope in Chile has been tasked with spectroscopic analysis to determine its composition. Meanwhile, space agencies are scrambling to repurpose satellites and probes to gather additional data. NASA's James Webb Space Telescope, with its unparalleled infrared capabilities, is being repositioned to study the object's thermal signature. The stakes are high, and the pressure is on. But this is not just a race against time. It is a race against our own limitations. The logistical challenges are immense. Coordinating observations across multiple continents and orbiting satellites requires precision timing and flawless communication. Engineers at NASA's Jet Propulsion Laboratory are working around the clock to ensure that the Deep Space Network, a global array of antennas used to communicate with spacecraft, is prepared to track 3I Atlas as it approaches Jupiter. At the same time, teams at the European Space Agency are reprogramming the Gaia spacecraft, originally designed to map the Milky Way, to monitor the object's trajectory with unprecedented accuracy. The data collected by these instruments will be fed into supercomputers at the National Center for Supercomputing Applications in Illinois, where advanced simulations will model every possible scenario for 3I Atlas's behavior. Will we investigate systematically or let this opportunity pass? The choice is ours, and the universe is watching. Every decision we make, every resource we allocate, every hypothesis we test is a reflection of our values, our priorities, and our capacity for wonder. This is not just about 3I Atlas. It is about us. It is about whether we are willing to look beyond the horizon of our familiar world and embrace the possibility that the universe is far stranger, far more complex, and far more beautiful than we ever imagined. The scientists involved in this effort are not just researchers. They are pioneers, explorers, and dreamers. They are the embodiment of humanity's insatiable curiosity, and their work is a testament to our collective potential. But they cannot do it alone. They need our support, our engagement, and our willingness to ask the hard questions, even when the answers are uncertain. The public's role in this endeavour cannot be overstated. Citizen science projects such as Zooniverse's Atlas Watch are inviting volunteers to help analyse images of the object captured by telescopes around the world. Over 200,000 people have already participated, contributing over 5 million classifications that have helped identify subtle changes in the object's behaviour. Their efforts are not only accelerating the pace of discovery, but also fostering a global sense of ownership and investment in the mystery of 3I Atlas. Meanwhile, educational initiatives are bringing the story of the object into classrooms, inspiring the next generation of scientists and thinkers. Students in over 1,000 schools worldwide are learning about astrophysics, data analysis, and the history of scientific revolutions through the lens of 3I Atlas. Will we follow the data wherever it leads, or cling to comfortable narratives? The temptation to dismiss 3I Atlas as a fluke, an anomaly, or a trick of the light is strong. It would be easier to ignore it, to pretend that it doesn't challenge our understanding of the universe, but that would be a mistake. The history of science is littered with moments when humanity chose to ignore the evidence in favour of comforting illusions. Galileo was ridiculed for suggesting that the Earth was not the centre of the universe. Darwin was vilified for proposing that humans were not a separate creation, but part of a vast, interconnected web of life. Yet both were ultimately proven right, and their ideas transformed our understanding of the world. Three-Eye Atlas could be another such moment. It could be the catalyst that forces us to rethink everything we thought we knew about the cosmos and our place within it, but only if we are willing to follow the data, no matter where it leads. The consequences of ignoring the evidence are stark. In the 19th century, the discovery of canals on Mars by Italian astronomer Giovanni Schiaparelli led to a wave of speculation about intelligent life on the red planet. However, many scientists dismissed the observations as optical illusions, and the opportunity to investigate further was largely squandered. It wasn't until the Mariner 4 mission in 1965 that humanity finally got a close-up look at Mars, revealing its desolate surface and putting an end to the canal hypothesis. Had scientists taken Schiaparelli's observations more seriously, the course of space exploration might have been dramatically different. Three-Eye Atlas presents a similar crossroads. If we fail to investigate it thoroughly, we risk missing a transformative opportunity to deepen our understanding of the universe. So, here's what I'm asking. Stay curious. Demand evidence, but remain open to what that evidence suggests, even when it's uncomfortable. Keep your eyes on the sky and your minds open to possibilities that our models might not have prepared us for. The universe doesn't care what we prefer to be true. It simply is what it is. And our job is to figure out what that is, as accurately and honestly as we can. This is not just a scientific imperative. It is a moral one. It is about being true to ourselves, to our capacity for wonder, and to our responsibility as thinking, feeling beings in a vast and mysterious cosmos. The mystery of Three-Eye Atlas is unfolding now. And we, the curious, have a role to play. Let's not waste it. Every night, millions of people around the world look up at the stars and wonder what lies beyond. 3. Atlas is a reminder that the universe is not a static backdrop, but a living, breathing entity full of surprises. It is a call to action, a challenge to our ingenuity, and a test of our courage. Will we rise to the occasion, or will we shrink from the unknown? The choice is ours. The universe is waiting. Let's not keep it waiting for long. In the coming months, as Three-Eye Atlas draws closer to Jupiter, the world will be watching. Children will stay up late to catch a glimpse of the object through their parents' telescopes. Teachers will pause their lessons to show live feeds from observatories. Politicians will debate the implications of the object's trajectory in hushed tones. And through it all, humanity will be reminded of its small but significant place in the cosmos. We are not mere spectators in this grand drama. We are participants, shaping the story as it unfolds. The mystery of Three-Eye Atlas is not just a scientific puzzle. It is a mirror held up to our collective soul, reflecting back the best and worst of what we are capable of. Will we embrace the unknown with courage and curiosity, or will we turn away, content to live in the shadow of our ignorance? The answer will define us, not just as scientists, but as a species. The universe is watching. Let's give it something worth seeing.